Gases, Part 2, Charles' Law and Gay-Lussac's Law. In this video, we will apply a submicroscopic model to explain the behavior of gases, and we will predict the pressure or temperature of a fixed amount of gas at constant volume and predict the volume or temperature of a fixed amount of gas at constant pressure. Let's get to it. Take a moment to consider this. Sure, you probably know that the hot air balloon floats because the hot air is lighter, or more accurately less dense, than the air around it. But why is the hot air less dense than the colder air? To answer that, we need only to consider the kinetic theory of matter. As the particles inside and outside the balloon are bouncing around at atmospheric pressure, they bump around at a certain rate of collision. If the particles are moving around faster, because their temperature and therefore their average kinetic energy have increased, then they will need to spread out and increase their volume and the space between them to maintain that constant pressure. This means that as the temperature of a gas at constant pressure increases, then its volume also increases. This observation is known as Charles' Law, which states that at a constant pressure for a fixed amount of gas, the volume and the Kelvin temperature are directly proportional. Directly proportional means that as one variable increases, the other increases proportionally as well. For example, if the volume is doubled, then the Kelvin temperature is doubled as well. Or if the temperature is cut to a tenth, then the volume will be dropped to a tenth as well, as long as we're talking about Kelvin temperatures. To represent Charles' law as an equation, it becomes V1 over T1 equals V2 over T2, where V1 and T1 are the initial volume and Kelvin temperature, and V2 and T2 are the final volume and Kelvin temperature. Remember, these temperatures must always be in Kelvin. The volume units could be any volume units, but they must be the same on both sides of the equation. Here's a sample problem that can be solved using Charles' law. A balloon filled with air is cooled, presumably by this baby penguin, from 315 Kelvin down to 295 Kelvin. If its original volume is 5.5 liters, what will its volume be at the lower temperature? Pause the video for a moment and solve the problem yourself. In this problem, we'll need to solve the equation for V2, the final volume. By cross-multiplying Charles' law, we get V1 T2 equals V2 T1, which we can divide each side of the equation by T1 to get V2 all by itself. So we will have V1 times T2 divided by T1. If we substitute the numbers and their units from the problem, we get 5.5 liters, V1, times 295 Kelvin, T2, divided by 315 Kelvin, T1. The calculation, rounded to two significant figures, is 5.2 liters. Here's another problem. A gas at 89 degrees Celsius occupies a volume of 0.670 liters. At what Celsius temperature will the volume increase to 1.12 liters? I'm going to remind you that no matter what, when you use the gas laws, you'll have to be using Kelvin temperatures. Pause the video for a moment and work on a solution yourself. Here's what I've got for this problem. The final temperature, T2, is what we'll need to solve for in the equation. Before I go any further, I'm going to convert the 89 degrees Celsius into Kelvin by adding 273. That gives me 362 Kelvin for T1. Solving for Charles' law for T2 gives me V2 T1 over V1. Substituting the known variables produces 1.12 liters times 362 Kelvin divided by 0.670 liters, which is 605 Kelvin. Since the question wants the temperature in Celsius, I'll convert 605 Kelvin into Celsius by subtracting 273, which is 332 degrees Celsius. Have you ever watched one of those perpetually drinking bird gizmos? It drinks, stands up, falls over and drinks, and the whole process goes over and over. Did you ever wonder what causes the drinky bird to fall over and continue to drink? The red liquid is pulled up his neck, which makes him top-heavy so he falls over. How the liquid is pulled up is because of a decrease in pressure inside his head. That decrease in pressure is the result of the cooling of his head as water evaporates off his felt face and beak. That is another directly proportional relationship, where a decrease in temperature causes a decrease in pressure. To explain this using kinetic theory, we'll see that if the space for the gas particles isn't changing, but the particles slow down, then they'll collide less often. This observation is known as Gay-Lussac's law, which states that at a constant volume for a fixed amount of gas, the pressure and the Kelvin temperature are directly proportional. So if the pressure is doubled, then the Kelvin temperature is doubled too. Or if the Kelvin temperature is cut to a third, then the pressure will also be cut to 1/3. Representing Gay-Lussac's law as an equation is P1 over T1 equals P2 over T2, where P1 and T1 are the initial pressure and temperature in Kelvin, and P2 and T2 are the final pressure and temperature in Kelvin. As long as you use Kelvin for the temperature and the same pressure unit on both sides of the equation, then you'll be good to go. So here's a problem that we can solve using Gay-Lussac's law. A 25 degrees Celsius pressurized oxygen gas canister is taken up a mountain where the temperature drops to negative 10 degrees Celsius, and the pressure in the canister drops to 3 atmospheres. What was the original pressure of the canister at 25 degrees Celsius? Pause the video so you can solve this problem for yourself. Here's how I solved this Gay-Lussac's law problem. We need to find the original pressure, so that is P1 in the equation. Solving the equation for P1 gives P2 T1 over T2. We can't use these Celsius temperatures, so we'll need to make them Kelvin temperatures. 25 degrees Celsius is 298 Kelvin, and negative 10 degrees Celsius is 263 Kelvin. Now we can substitute 3.00 atmospheres for P2, 298 Kelvin for T1, and 263 Kelvin for T2. This calculation ends up with 3.40 atmospheres as P1. Thank you again for watching this video. We applied a submicroscopic model to explain the behavior of gases. We predicted the pressure or temperature of a fixed amount of gas at constant volume, and we predicted the volume or temperature of a fixed amount of gas at constant pressure. Adios!